Okay, let's continue today's lecture and we'll decide what we're going to do about next week, Thursday. Okay, all right. Quick review what we have learned so far. Last time we have learned how we're going to design a section with given geometries. So if you see my screen, this is from last lecture notes. And if you haven't muted yourself, please do so. Unless you have questions, raise your hand. But what we have talked about so far are the analysis of singly reinforced section, the analysis for doubly reinforced section. What do you mean by analysis, right? Analysis meaning we know the section and we know the reinforcement, simply trying to find out the capacity of the section or the design capacity of the section, compare that to the required apply moment and make sure that the design have met the requirement. And then we move on to design. And there are two levels of design here. One level of design is we know the section size is fixed. We need to provide a reinforcement to that section. And next level is we don't even know the section. We don't have anywhere to start with. So today we're going to talk about how we're going to design a beam with known section. That means the only thing unknown is about reinforcement. And right now at this moment, several things should pop up in your head, right? About the reinforcement. What are the unknowns? First of all, total area reinforcement, it is unknown. We don't know how much reinforcement area, in terms of area, that is needed. Second, if we know the area, how many bars we need to put in the section? Can the section accommodate such number of bars? So all these has to be considered. All right? So we started with a simple problem last lecture with a simply supported beam and applied load of 1.2 det, 1.6 light, and the total applied moment is 145 kip-foot. And the section size is a width of 12 inch, height of 24 inch, and we have a concrete 4 KSI, yield strength is 60 KSI. We're simply trying to find out how many bars we need, right? So where did we start? We start by doing the design philosophies, right? So design capacity, which is phi mm, phi is the strength reduction factor, mn is nominal moment resistance, has to be greater than or equal to mu, where mu is applied moment. Okay, so this way we start from the left-hand side phi, stress reduction factor, and we say that let's assume 0.9 to begin with, and that is a big assumption. All right, that's a big assumption, meaning I assume the steel yielded, and in addition, I also assume the strain in the steel has exceeded 0.005, right? Then I carry this equation, in, okay, and then find out that I need to satisfy my required moment, which is mu, and AS should be bigger than or equal to this equation right here. And the mu is a required moment, which is 145 kip-foot. Okay, and now still there are several things that are unknown, right? Now we have phi figured out fine, but we have Fy figured out fine because the yield strength of the bars, right? The only thing that hasn't been figured out is this lever arm. And this lever arm contains two parameters. One is ds, that is the depth of the section. And when we say the depth of the section, we actually need to know where is the bars locating at to find out the ds, isn't it? And we don't have any reinforcement information to tell us that. Now, the other thing is unknown is the effective compressive zone size A here. Why is that? Because we don't have reinforcement. We don't know how much concrete that it would take to balance out the tension forces. Okay, so these two are unknown. And then with these two unknown, we don't know the distance between the center of the compression force and to the center of the tension force. So the lever arm JD here is unknown. We have a solution though, right? We say that how about we approximate this lever arm as approximately 90% of depth ds. 90% of depth ds. So that's the first quick assumption we made. And on top of that, we say that now if you don't know ds, and now we have one layer reinforcement, we can simply use h minus 2.5 to give you that ds. And why 2.5? Because this is one layer of reinforcement. So we use 2.5. If it were two layers, we can approximately use 3.5 inches. So we select with one layer, and that is h minus 2.5 to give you the depth. And with that depth, we bring into the equation, and then we can calculate the reinforcement area. right? So we went down, talk about the AS, and then the AS has to be greater than or equal to 1.67 inch squared. 1.67 inch squared. Now with that, we can start to do design, isn't it? But not yet, not yet. We need to quantify the compressive zone A. So how do we do that? We let the compression equal to tension and assume it's still yielded, and we used the estimated area of reinforcement into the equation and find out the effective compressive zone is 2.46 inch. Now with that effective compressive zone of 2.46 inch, we got the steel area recomputed again that has to be greater than 1.59 inch squared. 1.59 inch squared. So what does it mean? What does it mean by 1.59 inch squared? That means that I need to provide enough bar that has a area reinforcement larger than this number. So I have several options, right? So I can either choose number 8 bars or choose number 9 bars. These are my favorite bars. If I choose number 8 and simply put 2 bars in a row, because now I look at it, it's only 12 inch in the width, right? So if I put 3, I may have to do the detail check, but I know for a fact, if I put number 8, I'm gonna be fine. I'm gonna be fine. So I put 2.8 in it, and I have 1.58, slightly less than the required area. Now I say, you know what? I don't want to bother checking the details. I'm just gonna put another size up, number 9, and put in the section I have 2 inch squared, way overkill, right? Way overkill. But I'm fine. I'm happy with the number. So now I'm left with what? I'm left with a section that is known because I have a height, I have a width. I also have 2 number 9 bars, and I also have a location of the bars. Location of the bars. What does it mean? It means that I'm dealing with an analysis problem. I'm dealing with an analysis problem. Okay, so now the design has been turned into analysis, meaning we have provided an initial preliminary design, right? So from this section, let's move forward. So A, which is effective compressive zone, equal to what? ASFY divided by what? Divided by 0.85 F prime C B. Okay, so let's bring the number. AS is 2 inch squared, Fy is 60 KSI, all right, divided by 0.85 multiplied F prime C, which is 4 KSI, and a 12 inch of width, 12 inch of width. So with that, A now I got is 2.94 inch, 2.94 inch. And this is the effective compressive zone given a 2 number 9 bars at location 21.5 inch of depth, 21.5 inch of depth. From there, I can get my actual compressive zone C equal to A divided by beta 1, divided by beta 1. Okay, so quickly, I have 4 KSI concrete. Ashton, you there, Ashton?
Yes.
Hey, how are you doing, Ashton? Doing well?
Yep.
Okay, so quick question here. So if I have 4 KSI concrete, what would be my beta 1 value here?
0.85.
Yes, exactly. That's correct. Thanks a lot. And now I can get my C, which is 3.46 inch. That is my actual compressive zone size. With that, what I'm going to do is whenever you see actual compressive zone size C, you should have strain diagram popping in your head. Every time we have C, essentially we're trying to do strain diagram. And why is that? You also need to see that we have epsilon Cu, which is the compressive strain of failure for concrete, and that is 0.003. So these two in pair because I want to find out the strain in the steel. And ladies and gentlemen, this is the T, okay? This is epsilon T, okay? That is the last layer of the steel. So I can quickly check the strain in the steel using the equation of the from this triangle. So epsilon T should equal to dt minus C divided by C and multiplied by epsilon Cu. Okay, multiplied by epsilon Cu. Now that gives me a what? 21.5 as a depth, okay, minus C, which is 3.46, and divided by another C, which is 3.46, and multiply the whole thing by epsilon Cu, which is 0.003. All righty. So now I got my strain to be a 0.0156. So at this point, let me try to find my next victim here. Evan, you there? Are you there?
Yes, I'm here.
Okay, so I got my strain steel to be 0.0156. Should I be happy about it?
Yes, because it is greater than 0.005.
There you go. So that just confirmed my assumed case. Thank you, by the way. And that is tension control. So phi naturally is indeed 0.9. That completed my assumption. Remember, because we talked about this. And now if you stuck with phi and quickly in your head should pop up this graph here, and the bottom level here is epsilon t. So there are two numbers, 0.002 and 0.005. And again, if my strain of steel is lower than 0.002, Christina, Miss Lee, are you there?
Yes.
Okay, so if my strain in the steel is lower than 0.002, what would be my phi value here?
0.5.
There's something in front of it. Oh, you're almost there. 0.5? Give it a hint. Is it 6? Is it 6 or 8 or 7?
0.65. Yeah.
There you go. That's right. So hold on 1 second before I let you off the hook. So if my epsilon t is greater than 0.05, what do I have here?
0.9.
There you go. That's right. So thank you very much. And then I can connect the lines, right? Connect the 2 points and give my linear interpolation lines, right? Linear interpolation lines. Okay. All right. So now that is my phi. So if you're wondering about the slope here, so simply I can say the slope is 0.9 minus 0.65 divided by 0.005 minus 0.002. So what I have here, top, I have 0.25 and bottom 0.003 multiplied by a 1,000. So I have 250 divided by 3. That is the slope. Okay. All right. So that is the slope. So with the slope, what is the equation for phi, right? So immediately I can say that if it's smaller than 0.002, that is 0.65. Now greater than 0.005, it is 0.9. Know that in between linear interpolation, how to linearly interpolate it, that phi should equal to 0.002 plus this k here, which is 250 over 3, multiplied by this number, epsilon t, whatever in the middle, minus a 0.002, and then period, done. This is when epsilon t between 0.002 and 0.005. Alrighty. So that is the interpolation equation in case you have forgotten about it, But we're all fine here because our strain has exceeded 0.05. So phi equal to 0.9, simply that. All right, so with that, I'm pretty happy. I say, look, I have everything under control. I can proceed to calculate my moment. So my moment Mn should equal to ASFy, which is tension force, multiplied by the lever arm. Again, lever arm should be ds minus half A. Now the difference is that I now know my reinforcement area is 2 inch squared, multiplied by yield strength, which is 60 KSI, then multiplied by ds, which is 21.5 inch, minus A. What is A again? Go back, find out. A is 2.94 inch divided by 2. That is half A. So what I got here, Mn, that should equal to 200.3 kip foot. Okay, save you the time for calculation. Always check me whenever you can. And then with that number, I can get my design capacity. So for those of you who have forgotten the word or terminology, this is design capacity, okay? Design capacity or design moment resistance or design flexure strength. So whatever you call it, but this is design. Whenever you see design, that is after factor, right? After the strength reduction factor. So that is 0.9 multiplied by 200.3 kip foot. And what I have here is 180 kip foot. Okay, so with this number, I check again with the required loading, that is 145 kip foot. So with this case, I say good. Okay, design is adequate. Design is adequate. Happy campers. All right. So am I done here? Am I done here? Okay, I'm gonna call my next victim, Brennan, Mr. Pooh there. Are you there? Brennan? Brennan? Is your mic working or I got a zombie there? All right, let me try my next one. Audrey, Mr. Powell.
Hello.
Hey, how are you, Miss Powell? So quick question here. So my design is adequate, right? So am I done here? Am I done here? Am I, all sad and let it go,
Yes.
You would think so, right? But let me ask a question. This is step number 5. If I want to crane it, if I want to lift the beam, what should I need to worry about?
Oh,
Cracking, right?
yes.
So check cracking, thank you. And that's a very good observation. Check cracking. So meaning when I say check cracking, meaning I need to see if I have provided enough reinforcement AS min. Okay. For those of you, this is the first time probably for you to see AS min, right? And if you forgot, AS min is what? AS min is larger of, the bigger one of 2. What are the 2 equations? What are these 2 equations? Top one, 3 square root f prime c divided by fy bwd. Bottom here, 200 over fy and bwd. Bring the number in, so 3 square root of 4,000 psi and multiply 12 inch of width and multiply depth, and this is ds, so I'm going to take 21.5 inch divided by yield strength fy. What is the number here? 60,000 psi. Everything's in psi, and this is what, 0.82 inch. And now this is 0.82 inch. No, 0.82 inch squared, because that's area. That's area, right? So the bottom equation here, I have 200 multiplied by 12 inch multiplied by 21.5 inch and divided by 60, again, 1,000 psi, and I have this number to be 0.86 inch squared. So which one should I take? David, Mr. Breton. Hello? Are you there? Or you're zombie in? David, Mr. Breton.
Hello, sorry about
Hey, oh, good to hear from you. And say, which one should I take? 0.82, 0.86?
that. 0.82.
Why?
Because you want to take the lowest minimum.
Why? Why need I to pick the lowest?
Because it's the minimum, the larger amount. Sorry.
Alrighty, that's okay. That's why I'm calling you guys, right? Because we always forgotten this minimum, it's inside this term here, but when we say minimum, we truly mean we need to pick the bigger one as the minimum value, right? So that's okay. You got it, David. So it's got to be 0.86. Okay, 0.86. And let me clear up my handwriting. Can be very confusing sometimes. So let's larger off. Okay, larger off. Alrighty. So I'm at 0.86 inch squared. What I have anyway, I have AS provided 2 inch squared. That is much larger than the AS min, which is 0.86 inch squared. So I'm okay. Alrighty. So the beam will not crack when I lift it up in crane. And now, in case you don't have a visual image, right? Let me help you. So whenever you lift up the crane, okay, you lift the beam up. All right, if you're ever on the job site, when you're trying to lift the beam up, what you end up having is that we have some pre-hooked already embedded inside the concrete. So all you have to do is hook it up to a crane, hook it up to a crane like that, and lift it like this. So when you lift like this, right, the self-weight of the beam is pulling it down like that. The self-weight of the beam is pulling down like that. So this is equivalently like a simply supported beam. And being that these simply supporting beam is the lifting spot, and then you are exerting a uniformly distributed self-weight on it to create a bending moment. So naturally, these region right here in the middle is so-called a constant moment zone. Constant moment zone. You should have learned that from mechanics materials class, or these sections, okay, where mostly the crack will happen. So AS means is simply to certify that, to ensure there's no crack, in these sections, okay? Alrighty, so now no cracking. I can lift my beam anywhere I want, which is perfectly fine. So again, am I done here? Am I done here? Chris Steinbach. Chris, are you there?
Yeah, I'm here.
How are you doing, sir?
I'm doing good this morning.
Alrighty, wonderful. So am I done here? Is my design okay? Can I tell the construction guys, hey, make the beam, put it over there, we're done. Can I do that?
No, would you still need to check the cracking moment?
Well, I did that already, right? By providing minimum reinforcement,
Right.
right? So that is done. How about the next step? So let me ask you the other way. So I have bars, right? How many bars I have?
We have 2 bars.
Two
under 9
number,
bars.
yes, 2 number 9 bars, right? So what is my beam width?
Your beam width was
What is B?
12 inches.
12 inches, right? So if I ask you to put 2 bars in the beam, do you think you can do that?
As long as I know how high they go. And you said 2.5 inches last time.
The concrete cover, right? So 2.5, all right. That's fine, but is that it? Can I put a bar in? What I forgot to check.
You need to stir up first.
Yeah, sure, I need to put the stirrups, right? And when I put the stirrups in, and when you're trying to build the cages or build a beam, you need to lower your reinforcement cage into the formworks, right? So the question is that, do you think this will fit in? Reinforcement cage, will it fit in?
I think we need to check it.
Right, that's right. So what we need to do is to check what? B,
Beam in.
yes, that's it.
Okay.
You got it, thanks. So we don't know, right? We need to check again. You say, Bob, when you select the reinforcement, you told us, let's go with number 8. I think it's gonna fit. And then number 8 doesn't do it. And then you say, let's pick number 9. You say it's gonna fit. And you put it in there. So it should fit, right? Well, that's in my head should fit. There are a lot of things I think should work and end up not working. So to make sure as a civil engineer, to make things safe, we need to check the code. So if you look in textbook, right, the table A5, and I have uploaded on Canvas, right? So you can find out that there are, oh, okay. Brandon just replied, no mic, unfortunately. Okay, that's all right, Brandon. We'll let you pass this time. All right, thank you. And then with table A5, if you look at it, okay, you have this number of bars and actually size of the bars, I believe, and number of bars, right? And then you can correlate to the beam. All right, now I want you to take a look at the table A5, but for table A5 here, the beam for number 9 bars and 2 bars should be 8 inch. So number 9, 2 bars should be 2 inch. Sorry, keep messing things up. Why? 8 inch. Okay, and what we provided here is 12 inch, much larger than the beam minimum. Okay, all right, so that means we're okay finally. All right, so now we are done. Now we're done. So at the final design, so finally, when I tell the construction guys, I say, look, guys, you need to make a beam for us. and I have a beam width of 12 inch, which is out of my hand. People told me to make that, and height of 24 inch, again, out of my control. And I do have control of the reinforcement, so please put two number 9 bars, okay, at the bottom of the concrete, have a cover 2.5 inch in one row, one layer only, okay, and then space them out. All right, so are we done here? Not yet. One more thing is that I need to tell the guys also, I need a concrete cover here, and say you need to find out the concrete cover here. And from last lecture in the detail, I would just put 2 inches here for interior exposure and all that nice things as a clear cover, CC. And I also have to compare the distance between the bars. And let's just say that that's just 3 things: 1 inch dB, right? And then 4/3 D aggregates. And again, we're using Rala ready mix, so D aggregates is 3/4 as a coarse aggregate. So this is 1 inch again. So this has to be maximum of the 3 dB is 9/8. What is 9/8? 1.125 inch. So which one prevails? dB dominance. So to be more precise, I say this distance has to be 1.125 inch. And then I have another bar here and clear cover 2 inches. Now you add the things up, the smaller than 12, that means I had to be greater than or equal to 1.125 inch between the 2 bars. So as long as I satisfy that, your section is okay. All right, then you are truly done. And that is the finalized section you're showing to the construction guys. Okay. All right. Okay. Any questions? Any questions you guys have from the audience? Are we all happy with this?
I have a question. What is
Go ahead.
dB equals something over 8?
This is 9/8. Sorry about my write up. Because dB is what? Bar size. What is the size for number 9 bar?
Ah, I see.
There you
I
go.
see. Gotcha. Thank you.
No, sorry about my write up. Okay, I cleared up.
I also
One-
have a question.
Yeah.
I kind of got lost how you got the number 8 for the beam minimum so quick.
Number 8.
'Cause
Okay.
usually it's like it's a formula you go over.
So it's a table
Oh,
A5.
from the
Okay,
table.
but let me show you, okay? I think I need to show you that. Give me 1 second. I need to log in my canvas again. It's a little bit long process today. Every time I try to log in, they ask me all this code and everything. Give me 1 second, okay? Have you gotten the textbook, by the way, Luan?
Yeah, I know how to get it. I was just I didn't like
No
saw
problem.
you
No
telling
problem.
us.
Yeah. So folks, if you haven't gotten a textbook, Luan got it, perfect. But if you haven't gotten a textbook, go to the files on this canvas on the course section and upload it yesterday, I believe. There's a image called table A4, M, and A5. Here's A5. All right. So we're dealing with number 9 bars. Do you guys see my cursor here? Do you see the cursor, guys?
Yes.
Okay, I assume you do. Okay, number 9 bars is 1.128 inch. And then this is 2 number 9 bars. So I got 8 inch right here. That's B minimum beam width. All right, and this is, be careful, this is interior exposure. That meaning 2.5 inch of concrete cover maximum, lowest 1.5 inch. Okay, and this is number 3, double leg stirrups, mean 3/4 maximum aggregate size. So even stirrups are fixed at number 3. Okay, so to use this table, you have to satisfy all these requirements. Has to be interior exposure condition. If it's not, cannot use this table. Has to be a clear cover 1.5 inch or a little bit smaller than this number. Higher than that, cannot use it. Number 3, double leg stirrups, meaning stirrup size has to be number 3. Is that? If it's not that, cannot use it. And has to be 3/4 aggregate size maximum. Okay, see that maximum can be lower than this, but cannot be bigger than this. If you have aggregates of 1 inch or anything that above this number, cannot use this table. Okay, so this table is only convenient when you have all these conditions met. All right, usually I have to say that usually in our class, most of the conditions I will make them match, but on the job site, not necessarily so. If it does not match, cannot use the table, what you do, you have to go back to the detailing lecture and repeat the process we've shown you guys before. To have to calculate it one by one, right? One spacing by one spacing. Okay. All right, folks, any other questions on this? Are we okay now? Guys, anything else? Anything going once?
The other maximum spacing of the bar, that's 4/3 DEFG. Is that what you wrote? Equals 1?
Okay, I really have to clean up my right. I'll give you 1 second. Let me share my screen and explain to you. You just I can see this. Okay, so let me. Do you see the screen here?
Yeah.
Okay, so it's 4/3 D aggregate D subscript AGG dot. So that is aggregate size. Okay, so we are using 3/4 aggregate size. Got it?
Cool. Thank you.
No problem. Anything else, folks? Are we okay? And I promise you guys
I
I'll work
have a
on my hand up.
question
Yeah. Sarah?
about the clear cover being
Right.
2 inches.
Right.
Where
So
did we get that from?
these, we have a table for it. These will have a table for it. And if you go to, just 1 second, all right, let me switch screens. Okay, I think this is a better way to do that. Okay. Do you guys see my screen? Sarah, do you see it?
Yeah.
Okay,
Yeah.
so this is on Canvas again. There's a file folder. You see files, and there's a screenshot called concrete cover ACI 31819, right? You click on it.
Yeah.
And you see this table right here. Do you see this
Yes.
table here? So there's table 20.5.1.3.1. This should be on the ACI code as well. So what we're dealing with here, concrete exposure, right? So let's say that if we have cast against and permanently in contact with ground, this is what we're dealing with. Okay. Now
Okay.
this table 20.5.1.3.2, the latter one are for pre-stress bars. We usually don't have pre-stress bar in this course. All of us should use the first table, which is non-pre-stress bars.
Okay.
All right. So
yeah,
now,
I was just confused because the other table said the clear cover had to be like 1.5 inches.
right. I provided 2 just for safety purpose. I think we have enough beam width anyway, because the table is 8-inch, right? And we have 12.
Right.
It's much
okay.
higher than the number. So I just throw in the 2. I think that's going to be fine. But to be sure, you can take a look at the table, right? Let's just assume we have a beam, interior beam. That means not exposed in the weather. Do you see that? Not exposed in the weather or in contact with ground. So it's interior hanging in the ceiling per se, right? So if it's a beams right here, right? Beams, column, pedestal, and tension ties, or have beams right here, right? And have a primary reinforcement, right? Primary reinforcement, okay? And primary reinforcement meaning like regular reinforcement. And what we have here, 1.5, right? There we go. Okay, so for in the exam, I may play tricks, right? I say in the exam, if it's exposed to weather or in contact with ground, and usually we're using number 8 or number 9 bar, so that falling in this category, usually it's 2 inches.
Okay.
All right, so that's why I throw in 2, because 2 usually is safe. 2 is bigger than 1.5, right? But only if I have provided enough beam width that is much larger than the number I picked up from table A5.
Okay.
Yeah, is that clear?
Yes, thank you.
Okay, good deal, no problem. Anything else, folks? This is very important that we have all good questions. These are very good questions, okay? You need to know how to use table 20.5.1.3.1, very, how to say, familiarize with this table. And also you need to know how to use this table A5 to find out the beam width proficiently, okay? That's your future jobs, all righty? Okay, so let's switch back to my write-up and let's continue, okay? So give me 1 second here, mirroring in. All righty, so with that, I'm pretty happy. I said, look, folks, I have a very good outcome of this design problem, right? And I want to take a look at another problem like this. I want to take a look at another problem like this, but the structure is going to be a little bit different. Structure is going to be a little bit different. So example number 2. Example number 2. Okay. And now instead of simply supported beam, I have a cantilever. I have a cantilever. So I have a beam sticking out from the support. Okay. And then I have distributed load, right? And the distributed load looks like this. Boom, 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 boom on top of it. And then this is dead load. And then I also have a live load that concentrated at the end of it. And I call it P because it's concentrated, and this is PL, live load. All right, live load. Okay, now, to be a little bit more tricky even, I say, look, for this, okay, for this, omega D, which is the dead load, is only self-weight, just the concrete. All right, and then PL, which is the live load, okay, equal to 5 kips. 5 kips. And I'm doing a design with given section. All right, I'm doing a design with given section. So I say, look, the width of the section is fixed, and old friend 12-inch, 1 foot, and I have a height of 2 feet. 2 feet. These are my section properties. And my concrete is 4,000 psi concrete, old friend, and it's grade 60 rebar, which means 60 ksi yield strength. And to make our life easy, and I say the stirrups, number 3, and interior exposure. All right, let me pick my next victim among the roster. So who's on my list? I've done A and D. How about Henry? Scooby. Henry, are you there?
Yeah.
Hey,
Yep.
how are you doing, man?
Oh, can't complain. You?
Okay, good deal. So I have a stirrups number 3, interior exposure, and I was very excited. Well, I'm always excited, but I was very excited when I hear these two. Why is that? Because we can do what? Just what we just said here. We can use what?
Number 9 bars.
Well, yes, but more importantly, we can use table A5.
Oh, 5.
Is that right?
Yeah.
Right, that's very important. Okay, good. Thanks a lot, Henry. So now we are set. In a way, it's a simple question, right? Now, I want to put bars in, right? Before I do anything, I want to put a bar in. So in the exam, and you will see this, I promise you 100% you'll see this in the exam. And let me pick my next victim, Jordan. Miss Stoddard or Mr. Stoddard. Jordan, are you there? Or mic is working or not? Jordan? You there, Jordan?
And you said Jordan Stoddard, right? Not me.
Yeah, no, I said Jordan Stoddard. Jordan Stoddard? Okay. Your mic is working or your mic is not working, Jordan? All right, well, sorry, may have a technical problem. See the text message. I don't hear you, Jordan. Might have to get your mic fixed, but we have one online lecture only, all right? So don't worry about it, okay? But you're there, I'm very happy. Katie, Miss Fisher, are you there? Katie, Miss Fisher. Okay, good deal. So quick question for you. Now, pay attention. I'm being a little bit tricky as Bob, right? So I'm gonna put a reinforcement in it, right? And in the common case, the simply supported case, I'm gonna put my reinforcement at the bottom here in the section. Is that right?
Yeah.
So in this case, it's a cantilever. So should I put my reinforcement here, or should I put my reinforcement at the top?
At the top?
Why is that? Good answer, by the way. Why is that?
I'm not sure.
I'm not sure. It's like Russian roulette, right? It's not the bottom. Apparently, you made that clear, right? So the thing is that think about the bending moment, right? So if I'm pushing the beam down like this, right? Can you imagine, right? So my bending moment will be like negative. Is that right?
Yeah.
Okay. So if a bending moment is negative, Now, which part would take care of tension, top or bottom? At the end section right here. Bending this way. You look at the arrow, right? It's like pulling things out and going to compress it here, right? So which side should see tension, top or bottom?
Top.
Top. There you go. Thank you very much. So that's where the tension's at. That's where my bar is going to be at. Okay. So folks, I will, and you probably have seen this from your sorority or fraternity houses, right? I will ask you if you have a cantilever beam like this, draw me, and then I'm going to spit out like that, right? Very strict question. And I say, okay, in A, this is where A is at. Okay, and draw me the reinforcement configuration, right? At the end of the design, where it goes, since it's a negative bending moment, so it's going to be on top. Don't mess it up, please. Okay, don't mess it up, please. All righty. Okay, so hard question all over. Now I can start looking at the question now. So solve it, right? So design, basically. Design, and this question here is design for AS. And apparently AS is on the top, and we don't know the number for it. Okay, so now I'm going to do design. Say design, and here's the first thing. I have dead load, self-weight, right? Omega D equal to what? And this is only self-weight. So I need to figure out the self-weight. And to figure out self-weight, I have 150 pounds per cubic feet as a density of the concrete. This is specific weight of concrete. Specific weight of concrete. Okay, it is not exactly density. Density is math, right? Specific weight is the gravity effect, right? Gravity effect. So I want to calculate the self-weight. All right. So I need to multiply something. Why is that? Because I look at the section right here, right? And I say per foot. And this is 3D, right? So per foot, I have a section like this. Per foot. Per foot, right? I have a width of B equal to 12 inch, height H is 24 inch. And all these concrete, the solid concrete would take the weight, right? So if I say omega D, that is the dead load per foot. And I want to convert that. So what I do is I need to convert that by multiplying a 12 inch of width and multiply a 24 inch of height. Okay, but don't forget this is per foot. Okay, and I want to convert unit to foot. So this is inch, this is inch. So 12 inch per foot, 12 inch per foot. And that gets me the dead weight. Okay, the dead load. All right, so after calculation, I got my dead load of 300 pounds. Pay attention. After unit conversion here, this thing comes out, has to be what? Foot squared. So foot squared here, foot cube at the bottom. I left it with a foot at the bottom. Pounds stay the same. So 300 pounds per foot. 300 pounds per foot. And that's how I calculate the dead load. Okay, so now I look at my beam. I say, look, the beam has simply converted into a very straightforward problem. That is, I have a dead load of omega D distributed along the length of the cantilever, and omega D equal to a 300 pound per foot. And I also have a concentrated live load, and that is what? 5 kips. 5 kips. And that's what I have. That's what I have. But now with this, I do not necessarily get my applied moment mu here. Remember, mu equal to 1.2 dead moment plus 1.6 live moment. So I need to decompose this too, right? So this equal to a distributed load only, constant moment, right? Plus, and then live load only, constant moment, right? So I drew the moment diagram like this, and the moment diagram looks like a negative values like that. And then I have a concentrated, right? This is also a negative moment diagram like that. Okay, so what is this value here? Fahad, are you there, Fahad? Fahad?
Yes, sir.
Are you there?
Yes.
Good deal. So if I have a length, total length of here, say 20 feet, And sorry if I did not provide that at the beginning. This total length is 20 feet here, guys, 20 feet. So I have 300 pounds per foot of the distributed load. What will be the moment caused by the dead load? How to calculate that? Fahad, are you there? Do you hear me? Hello, guys. Anyone? Can you guys hear me?
We can hear you.
I'm
Yeah, we
still
can hear you.
connected, right? Just make
Can
sure I'm
hear
still
you.
connected. Okay. Thanks. Fahad, are you there? Are you disconnected? Are you there? Yes. So what will be the moment here, MD, at the end of it? So that equal to the total force applied on the cantilever, right? What will be the total force applied on cantilever from the dead load only? Let's do a separation, right? Don't worry about the live load, just do the dead load. What is that? Distributed load omega D, right? Multiply what? Multiply by the total length, right? That is the total force by the dead load. Now I got the force, I need to know the distance, okay? And Fahad, in case you forgot, and the distance is half L, right? So that is the moment applied to it, okay? Thank you, by the way. And this is 300 pounds, sorry, 300 pounds per foot, and multiply by 20 feet right here, and multiply by a 20 feet divided by 2, and that is the total moment I have from the dead load. All right, so the quick calculation tells me that I have this number, and guys, please help me check this number, okay? I may have made a mistake here. 72,000 pounds multiplied by foot. Okay, now this is only the dead load. I'm looking at the live load here, right? Looking like the live load here. This is 5 kip, and the distance is 20 feet. So live load is much easier. Live load is only 5 kip multiplied by 20 feet, and I can write out directly, right? So live load is 5 kips multiplied by 20 feet. I got about 1,000, 100. See, 50, 20. Yeah, so actually it's 100 kip feet. 100 kip feet. All right. So top, the dead load is 72,000 pounds feet. So 72 kip foot.
Dr. Wu.
Yeah.
I got we got 60,000.
Yeah.
Oh, geez.
Yeah,
Yeah,
we got
It's right here,
60,000.
60, yeah,
70
so my
Yeah, 72
mistake.
multiplied by that factor of
Yes.
1.2.
Thank you guys for catching me. Appreciate that. Really appreciate that. Yeah, I told you guys, I always make mistakes. Not very good at algebra. All right. Thank you so much. Okay. So now that is dead load, 60,000. I think, let me just double check. Okay. 320. Yeah, you're right. 60 kip foot and 100 kip foot. So mu should equal to 1.2 md and 1.6 ml. That is 1.2 multiplied by 60 kip foot, and plus a 1.6 multiply 100 kip foot. And as you guys have spotted, I made a mistake there with 72 kip foot after the factor, and then I got 160 kip foot after the factor from the live load, and the total applied moment should equal to a 232, and I think this is correct, kip foot. Thank you again. So that is applied moment. Alrighty. So you see in the real exam, this is only beginning of the problem. This is only the beginning of the problem. It takes more time, isn't it? It takes more time. Okay. So I'm running out of time today. I'm gonna let you go, and we're going to talk about the design for this for the rest of the problem. Okay. And we'll meet again tomorrow, 1 o'clock online again. Sorry about this again. And then we can go over the design and talk about how we're going to solve the problem with the career fair next week. Okay. If you have any question, please stay behind. Fahad, I need you to stay behind. We need to talk about the other things. And let me see here. No, I think the rest of the kids were fine. Yeah. All right. So feel free, if you have any questions, stay behind. We can talk about. And Zhang Xiang, sorry, I forgot now. Xiang Zhang, please stay behind as well. I remember you have a question. We can go over them, okay?